Hello and welcome to lecture 26 on convex analysis. Okay, so yesterday we talked about the main iteration theorem, or Krasnodębski iteration theorem, which says us that a simple fixed point iteration for a non-expansive operator may still converge to a fixed point if there exists one, and the sequence generated by the iteration is asymptotically regular, meaning that the distance between two iterates goes to zero. And then we also introduced the notion of averageness and seen that then we can prove a similar result, but also which is valid for a larger range of relaxation parameters, including the relaxation parameter 1, which is the exact fixed point iteration. And before we proved the Krasnodębski iteration theorem on the relaxed man iterations, so we like under-relax a little bit, don't do the full fixed point step, but a little less. I had some during the lecture yesterday, I was a little bit insecure and it had several steps. In the end, it turned out that all the steps were correct as written. I just didn't see it at that time. So, but now I uploaded the corrected version of the or an extended version of the lecture notes, and so you could see a little more explanation about these steps. Okay, so that was kind of general stuff about non-expansive operators and firmly non-expansive operators, and we already know that the resolvent of a monotone operator is firmly non-expansive. So it's a prime prime example for the application of the Krasnodębski Mann iteration. Okay, and this is then called the proximal point algorithm. 26. Oops, I wanted to probably take the black one. So the proximal point algorithm. So it's just if we have a monotone, then you just x0 kind of arbitrary in x. So this, of course, maps multi-valued g from x to x, some initial value, and then you just iterate xn plus 1 is equal to j, and then I introduce a step size here, let's say gamma a xn, gamma positive. So that's already the proximal point algorithm. So why is it called proximal point algorithm? It comes from the fact that if a is a subgradient, then you recall that j gamma subgradient is nothing else than the prox of gamma times f. So in this case you see that xn plus 1 is simply the proximal operator of gamma f applied to xn. So this is the origin of the method, and it comes with an interpretation of successively minimizing f, but this is basically the same thing, but just applied or just used with a resolvent instead of a proximal operator. So it's a little bit more general than that. So proof of conversion of the proximal point algorithm for convex functions, you can rely on descent arguments, so the objective value, for example, is decreasing of iterations. If we now talk about monotone inclusion, there's no such notion of function value, because the problem here is 0 in ax that you want to solve. So there's not really clear what kind of values we can track actually. So it's not really so the proof has to be different. It's not able to rely on descent arguments. Okay, so since we know that resolvents are firmly non-expansive, we could just start right away and write down the theorem. I introduce one more term and then proof, or two more terms, and then two more notions, and then we're going to prove that, because then we can also check out in which cases we even have linear convergence. So the definition which we're going to use is again one for monotone operators. It's the so-called co-coercivity. So having a subset of our x and a t which maps d to x, and then we call t beta co-coercive, with some beta positive. If beta t is firmly non-expansive, That's one way to put it, and let's write it out. This means for x and y in D, it holds that the inner product x minus y tx minus ty is bounded from below by beta tx minus ty squared. So that is coercivity. And note the difference between strong monotonicity. So having this inner product here positive, that would be monotonicity. Having it larger than the distance of x to y squared times the constant, this would be strong monotonicity. But if you put tx minus ty here, then it's called beta coercivity. And note that this only makes sense for single-valued operators, right? If for multi-valued, you can just not put different things here, and it's most likely not to work at all, actually. So of course, one immediate consequence is, so if t is beta coercive, then you get that beta times tx minus ty squared is smaller than this inner product here. And then of course you could apply Cauchy-Schwarz, and you will see that you can now divide by tx minus ty, that this norm here is smaller or equal than 1 over beta times x minus y. So if t is beta coercive, it's also Lipschitz with constant 1 over beta. So hence t is 1 over beta Lipschitz. Okay. But the other way, the other direction does not hold. It's kind of fair. Yeah, let's keep it like that. Okay. Good. And then there's a connection with strong monotonicity of A and the coercivity of the resolvent, and it goes like this. Proposition 26.2. So A is monotone, and beta is now, it can also be actually beta equal to 0 would be allowed, then it's just a non-condition basically. Then we could say that A is beta strongly monotone, if and only if the resolvent JA is beta plus 1 coercive. Yeah, that's it. And especially JA is beta plus 1, sorry, is 1 over beta plus 1 Lipschitz. So you see that if you have a strongly monotone operator, then the resolvent is even a contraction, which is nice. Okay, so and also the proof is not difficult here. So how does that go? So A strongly monotone with constant beta. Let A be beta strongly monotone, and having U equal to J of AX and V being equal to J of AY. So let's decode that in terms of inclusion. So remember that the resolvent here is identity plus A to the minus 1 of Y. So now we can just bring that to the other side here and see that, so this is if and only if we have V plus AV, therein is Y. And the same here, bringing the resolvent to the left hand side, you have U plus AU contains X. Okay, we rewrite it, so bringing U to the other side, having X minus U is in AU, and V minus Y minus V. Y minus V is in AV. Okay, and actually there's a typo in the lecture notes I'm going to collect. This is of course V here. And then by strong monotonicity, we get that beta times the difference of the arguments, so u minus v squared, is smaller or equal than difference of the elements in the operator, which means x minus u minus y minus v times difference of the argument, which is u minus v. And you see here, this here is nothing else than x minus y minus u minus v. So this is x minus y, u minus v, minus norm u minus v squared. So there you have it here, right? This goes over here, so this is then if and only if beta plus 1 u minus v squared smaller equal the inner product, x minus y u minus v, and that's it. And this also works the other way around, and so this proves the claim. Okay, and then finally, before we come to the first convergence theorem for the proximal point algorithm, I finally define what do we mean by linear convergence. So actually I've used it already, but I forgot to define it, and now let's do that here. The definition now, if we have xn converging to x bar, we say xn to x bar linearly if there is some eta between 0 and 1 such that the distance of x n plus 1 minus x bar is a factor of eta smaller than the previous one. So that's what I mean by linear convergence. And of course you can just iterate through and get it to xn minus x bar smaller equal eta to the n x0 minus x bar. So this is this is then called linear convergence, and also this is here this eta is the rate of linear convergence. Okay, this is standard notation, and then that's just something which you probably already know from a numerics class, for example, or optimization class. Okay, good. So now comes the first theorem on convergence of the proximal point method, and it's just collecting things you already know, and then we have a proposition. 26.4. So we need A maximally monotone and gamma positive and 0 arbitrary in x, and iteration xn plus 1 is j gamma a x n. And then we have first so first thing is if the inclusion has solutions, has a solution, then xn converges to one of them. So that's the first thing. Without existence of solution we can't prove anything, and it's not really clear that there should be some. So for example, the A could be constant 1 then or constant, then it would be still maximally monotone, but there would be no solution. But as soon as there is one, the situation will catch one of them. And then if A is strongly monotone, actually with constant beta, now I don't care about the constant here, then xn converges to the unique, or converges linearly to the unique solution of 0 in AX. Okay, that is that. And probably the only thing which is really not the only thing, so we can just collect all everything we know, and maybe I take the opportunity and actually prove that fixed points of the resolvent are solutions of the inclusion. I'm not sure if you already proved that, but so now here it is. So if we have x star as a solution, then we also have x star is in gamma a, 0 is in gamma a x star. Of course, we can just multiply both sides by gamma, nothing happens, but we can also add x star on both sides, and this x star is an x star plus gamma a x star, which is identity plus gamma a x star, and this is if and only if x star is j gamma a x star. So that's simple. So fixed points of the resolvent are exactly this is also if and only if here are exactly the solutions of the inclusion. Okay, and then we have now so that's one point, and the second point is we can use what is it, proposition 24.9 tells us that J gamma A is fermion expansive. Okay, proposition 25.7 was it, shows us that then J gamma A is 1/2 average then, because this holds for all fermion expansive operators. And then proposition 25.8 with we had this relaxation parameter lambda n, it should be smaller than 1 over this guy here, 1 over 1/2, which is 2, and so we can take 1. And this shows the claim. So this is for the first point. Maybe this is a general observation up there, and this here is now the first point. So we have everything already. And the second part is even simpler. In the second part, we even know, so by proposition 26.2, J gamma A is let's say it's 1 over beta gamma plus 1 Lipschitz if A is beta strongly monotone. Okay, and so this means that J gamma A is a contraction, and claim follows by Banach's fixed point theorem. Okay, that's it. Okay. Good. So the full claim follows actually also the uniqueness, of course. So if you have now the contraction here, we know that there's a unique fixed point, but we know fixed points are exactly the solution, so there's a unique solution. So Banach's fixed point theorem tells us everything we would like to know here. So another observation is, this is now hints into a disappointing direction. So you see that the larger the gamma, the better the convergence rate here. This is the convergence rate of linear convergence, 1 over beta times gamma plus 1. So the larger the gamma, the better the convergence, the faster the convergence. So you can kind of do one step with a very large lambda, a very large gamma, and have almost solved the problem already. This sounds strange, but on the other hand, it's not strange because, well, if you want to calculate one step of the method, you have to invert or solve a monotone inclusion, right? Applying this is solving a monotone inclusion. So it doesn't really sound like this is actually an algorithm. It's not really, why should this work? So if you could invert this, then you maybe even could be able to invert A, and then that would be the solution. Just the solution of the, so in theory, the solution of 0 is in AX is just take every x which is in A to the minus 1 of 0. Sure, that's A to the minus 1 of 0. But that's always the case for all problems finding roots of equations. So 0 is f of x, just invert f. So what that's it's usually not that simple. But here the question really arises, why do we even consider the proximal point algorithm at all? And I will start showing this at the end of the lecture, and the next week, in our last week, we will develop this into a more larger framework. Okay, but first, another thing. Now here we used fixed gamma. The step size is the same always, and this is probably a little bit restrictive. Sometimes one would like to have more flexibility to adjust the step size to something. And here's a theory which again shows you that this works, and it's just a little bit of a different proof technique, because we can't rely on this non-expansiveness or averageness result when the constants vary with the iteration. So, but it still works. So here's theorem 26.5. And then you have a maximal monotone. 0 and a x has solutions. These are our assumptions. And also gamma n positive, such that gamma n squared let me see, that's the typo actually. Gamma n, the sum over gamma n has to be infinity. So the gamma n, oh boy, 2 times. Okay. And again, iteration xn plus 1 is j, now gamma n a xn. That's the difference here, there's no gamma n. And each step we take a different step size. So and then xn converges to solution of 0 and ax. That's it. Okay, and the idea here is that the idea, so it's this proof, and it's often the case. Life gets simpler if you introduce auxiliary variables. Here the auxiliary variable is un is equal xn minus xn plus 1 over gamma n, because this is exactly in a of xn plus 1. This is because since xn plus 1 is in I plus gamma n a to the minus 1 xn. And if you just bring this over here and subtract the right things, divide by gamma n, you end up here. Okay, and then another thing is also you have that xn plus 1 minus xn plus 2. Also this comes just from here. It's gamma n plus 1 un plus 1. This is just from this is just the definition of un, but evaluated at n plus 1. Okay, so these 2 things we're going to need. So we're going to need this definition and that definition, and then we use monotonicity. Monotonicity. So by this inclusion, you're also going to use this inclusion over there. And see that 0 is smaller than the inner product of xn plus 1 minus xn plus 2. So these are 2 things, 2 arguments, and then things are in that there are then un minus un plus 1. Okay? But of course this still holds true if we multiply by 1 over gamma n plus 1. Doesn't affect the non-negativity. So, but then we have this guy here. Do we take this guy? Yeah, we take the guy here, yeah, on the left hand side. Xn plus 1 minus xn plus 2 divided by 1 over divided by gamma n plus 1. It's exactly un plus 1. So this here is nothing else than un plus 1 times un minus un plus 1. And this is un plus 1 times un minus un plus 1 squared. Right? And then again Cauchy-Schwarz on this inner product here gives us another norm un plus 1, and let us pull it out, and here we have un norm minus u. I have to be a little bit more careful with the bars and the u's. U n plus 1. Okay. Okay, and now that's interesting because we see this. So this is positive here. This is, of course, positive. If un is 0, then you would not do anything anymore. So this has to be larger than that. So what we can conclude is un is decreasing. Okay. Hence convergent, and you see it's a little bit along the lines than before, but not just not everything in one thing. Okay, so now so decreasing and hence convergent. So only the sequence of the norms is convergent. Now it's converged to some value. We don't know what it is. Hopefully it's 0, because then this would look like a solution here. But anyway, so now let's see fulfill 0 is an AZ. So let Z be one solution of of the inclusion. So then we have that Z is, of course, J gamma n a Z for any gamma n. Doesn't matter. Solutions are fixed points. That's it. Okay, now we use this firm non-expansiveness, and so try to estimate this guy here, xn plus 1 minus Z, and then, of course, here we can plug in the resolvent. So this is just a step. Here we can also add the resolvent, because Z is the fixed point of the resolvent at any, for any gamma n. And now firmly non-expansive gives us this is smaller equal to the difference of the arguments minus the difference of 1 minus j gamma n a xn minus identity minus j gamma n a z squared, and note that this is actually 0 because z is a fixed point of the resolvent. But anyway, and this here is actually xn minus xn plus 1, which is gamma times un. So this here is equal xn minus xn plus 1, and this is gamma n un. So we have here that this expression here is exactly xn minus z squared minus, and then this is under a norm squared, it's gamma n squared norm of un squared. Okay, so this shows us now that xn minus z is decreasing again, or put differently, xn is Fourier monotone. Fix j gamma. Yeah, let's do it. It doesn't matter. The solutions of the inclusion. So I don't have a notion for the solution set of inclusion, but it's the same thing here. So, but now I'm not sure. This doesn't tell us enough, I guess. So we only have these obvious things now. But what we get more is we also have this guaranteed improvement here. We know that the next difference is this thingy here smaller than the previous distance. So when we can sum this up, or telescoping it, whether, so it doesn't matter how you want to phrase it, and see that you get n, the sum from n0 to capital N over gamma n squared norm un squared is bounded by x0 minus z, for example. And then it's an argument like before, since the this thing here diverges, the lim inf of the norm un squared has to be equal to 0. But from where do we know that? From here, we already know that un is convergent. The norm of un is convergent. The lim inf of the norm is 0, so I can also get rid of this. Doesn't matter. The lim inf has to be 0, but the sequence converges. But since un convergent, we get that un converges to 0. So the norm converges to 0 and so on. Okay, and now xn is bounded. We also know that. We get that from here. Okay. Hence it has an accumulation point. Now let's call it x, just x. Let's call it x bar, no matter. So we say x n k, and let's call it +1 converges to x bar. So but then we have so u n k is an a x n k, okay, +1. So this is the difference of the un, but this goes to 0 and this goes to ax bar. Okay. And yeah, and so this proves that x bar is a solution. So all the accumulation points are solutions, and still open if the full sequence xn. So let's clear it. So every accumulation point is solution. This is what we get, but we would like to know that there's only one accumulation point. It sounds reasonable, but it's not clear yet. Yeah, so how do we do it? Yeah, let's assume that there are two. So one sequence xnk should converge to x, and another sequence xmk shall converge to y. And then we know that both these xnk minus x and xmk minus y, they both go to 0. And then we can write down that the inner product of 2 times xn x minus y, that's actually equal xn minus x squared minus xn minus y squared, xn minus x squared plus norm x squared plus norm y squared. So it's just fiddling around with the norm squares. So, and here the right hand side does converge actually. So the right hand side converges, so the left hand side has to converge. And if we now pass along the subsequences xn, nk and mk, so xnk to infinity in this equation here, and mk to infinity gives us that x minus y squared is actually equal to minus x minus y squared. So just do that, and you see this one here. So for one of the conversions, one term vanishes, the other stays, and this turns into either xn or x or y, and the others here then give you the negative norm is equal to the positive norm, and this shows us that actually x is equal to y. So it's a little bit comparable to what we've seen before in the conversion of the proximal point, but now you see that this gamma n doesn't really make a big difference. So of course, yeah, now one could go on and try to prove convergence of the dynamically relaxed and so relaxation parameter gamma lambda n varying, and also step size varying. And this will also work as far as I know for any step sizes. It should be no problem. Okay, good. I think it's time for the break already. Yeah, sure it is. So yesterday we've had this movie on mathematics of economy and finance. And also the math students made a video about studying math, just math, and I think it's awesome. It's on YouTube since Monday, I guess, and so I just showed now. So maybe you're gonna see some people you know here from TU Braunschweig. So please enjoy. It's about 3 minutes. It's 3 minutes, and then we come back to the lecture here.
Ihr denkt, das Mathe-Studium sieht so aus? Es ist nicht mehr ansatzweise so. Ich bin Lennart und ich werde euch jetzt zeigen, warum wir gerne hier Mathe in Braunschweig studieren. Kommt mit. Hier kennen sich fast alle Studierende untereinander. Hey.
Hallo.
Und auch zu den Lehrenden haben wir einen sehr persönlichen Kontakt. Die Türen sind immer geöffnet und die Dozenten sind da, wenn man Schwierigkeiten hat. Das ist die sogenannte Hängematte. Hier können wir lernen, arbeiten, aber auch einfach unsere Zeit verbringen. Hey Live.
Ach, hi Lennart.
Na?
Na, alles klar?
Ja, und bei dir?
Auch, klar, immer.
3 Semester bist du schon hier. Haben sich deine Erwartungen erfüllt?
Ich würde sagen, insgesamt schon. Also dieses logische Denken, das intensiv in so eine Materie eingreifen, so das intensive Verstehen, das waren auf jeden Fall Dinge, die ich erwartet habe und die haben sich in vollem Umfang erfüllt.
Ja, also ich glaube, das hast du mittlerweile auch schon festgestellt. Das ist was ganz anderes als in der Schule. In der Schule kratzt man einfach nur an der Oberfläche von dem, was Mathe eigentlich ist. Das geht hier viel tiefer.
Ja, also hier macht man ja auch zum Beispiel solche Dinge wie Programmieren. Also ich hatte gar keine Vorkenntnisse, habe noch nie programmiert, aber war alles kein Problem. Also wir wurden von Grund auf rangeführt. Und das fand ich eigentlich war auch eine coole Sache. Also dieses etwas in den Computer reintippen und man kriegt eine Lösung plötzlich. Das ist wirklich auch so eine Sache, das hat mich so ein bisschen auch nachhaltig fasziniert. Und was mich noch überrascht hat, ist, dass man hier wirklich viel in Gruppen arbeitet, also Aufgaben macht, lernt und so weiter. Also in der Schule habe ich doch einige Sachen so ein bisschen mehr oder weniger alleine gemacht. Das ist hier komplett anders an der Uni.
Ich finde, durch das Mathe-Studium hat man einfach eine ganz andere Art von Denken kennengelernt. Man sieht einfach in seinem Alltag so viel mehr Anwendungsmöglichkeiten dafür. Also überall kann man eigentlich Mathe benutzen, wenn man es will.
Ja, dazu eine kurze Story. Und zwar, ich habe letztens hier in einer Hängematte mit einem Kumpel habe ich mich hingesetzt und wir haben so ein Holzsteckspiel, Solitaire heißt das, gespielt und ich habe das früher nie hingekriegt. Er hat mir auch erzählt, er hat das früher nie hingekriegt und dann haben wir uns gedacht, Mensch, jetzt wollen wir es mal wissen und jetzt mal lösen wir das mal. Und da haben wir eben so ein paar Algorithmen für dieses Spiel uns überlegt, genau, und so ein bisschen geordnet, sage ich mal. Und plötzlich hat das Spiel funktioniert und plötzlich haben wir das Spiel gelöst. Und das war auch so ein Ultra-Erfolgserlebnis. Also für mich ist eben, sowas ist auch so, das ist die Essenz des Mathe-Studiums. Also man löst Aufgaben und dabei ist wirklich, man fühlt fast, wie man dabei quasi das tiefgründiger versteht, das Thema. Während des Semesters macht man quasi die Hausaufgaben schon mit den Freunden oder mit den Kommilitonen, mit Gruppen, wie auch immer. Und das ist auch so eine Sache, die wirklich mega cool ist im Mathestudium, dass man während des Semesters einfach schon so eine Art Klausurvorbereitung macht.
Ja, genau, und manchmal hat man einfach irre schwere Aufgaben, vor denen man steht. Aber wenn man die dann endlich geschafft hat, das ist ein so tolles Gefühl.
Da kann ich dir vollkommen zustimmen. Und wenn ihr jetzt Interesse bekommen habt, dann schaut doch einfach mal unten in die Beschreibung rein. Da haben wir ein paar Links und ich würde sagen, vielleicht sieht man sich dann ja irgendwann mal tatsächlich hier auch im Studium. Und bis dahin. Ciao.
So of course there's it's not the info box below here, but the info box of that video which you find in the YouTube channel of the TU Braunschweig. And spread the word. So I think it's a very nice video showing how studying works more or less, and gives a kind of, I think it's a very good impression of how that really is. So in case you know somebody who's struggling with a choice what to study and is interested in maths, just send the link and so that they can decide a little bit more qualified. Okay. So now we come for the practical aspects of the proximal point method. So inclusions like that here, as you see, in principle it's just inverting A. So, but in general this is hard. Proximal point replaces this problem by inverting identity plus gamma A, which can be as hard. But things may get simpler if we precondition the problem. So we have this A is multi-valued operator from x to x, monotone, or let's say maximum monotone for simplicity. And now consider we have another operator M, any operator, which is now from x to x linear. And let's say SPD, so symmetric positively finite. And I sometimes write this down like this. M is positive, it means symmetric positively finite. No, it's a symmetric, it's a self-adjoint operator. It's positively finite, meaning that all these inner products, x, mx, are positive. Oh, sorry, I need positively finite, not positive semi-definite. So positively finite meaning that this, and means here that this is strictly positive for x being non-zero. And actually this implies that M is invertible. Okay. And now we could kind of multiply this inclusion from the left or from the right by m, and the set of solutions will not change because this m is invertible. It's a bijection on x. It just kind of deforms our space in an invertible way. So what we do now is, for practical reasons, we're going to invert this inclusion from the left by m to the minus 1. So this here has the same set of solutions than that inclusion here. So this is just this is a set of elements in X, and you apply m to the minus 1 to all these sets, and you get a new set. That's what that says. So, okay, that's equivalent, but unfortunately, so even though m to the minus 1 is again SPD, this is true for symmetric positivity finite matrices, this inclusion here is in general not even monotone anymore. So even though SPD operators are also monotone in the sense of multivariate operators, they are. This is basically what is here. If you use linearity and this here, it shows you that it's even strictly monotone. But the multiplication of two monotone operators is not monotone anymore. We probably talked about that the matrix, for example, this matrix here, 0, 1, minus 1, 0. This one here kind of turns the R2 space to the left by 90 degrees, and it's still monotone, maximally so, because it's continuous. But if you apply this twice, you turn to the left and one more time to the left. So this squared here is the negative identity, and that's not monotone at all. So multiplying monotone operators doesn't give you a monotone operator again. And even multiplying two symmetric matrices doesn't give you a symmetric matrices, by the way, so this doesn't hold either. So it's not monotone anymore. In general, so maybe, of course, if m is the identity, then it is, okay, but anyway. But let's see that we can still treat this inclusion with our methods right now, and there I'll show you two different ways how to do that. So first, the kind of straightforward way, the way we probably also learned in a class on numerical methods for linear systems. So if, since this m to the minus 1 is also SPD, there exists a square root m to the minus 1/2, which means this is also SPD. So, and this means that m to the minus 1/2 times m to the minus 1/2 is m to the minus 1. And so for general matrices, taking square roots is a tricky business. A lot of things can appear. You have a lot of square roots, for example, in general, as far as I know. Yes, it is. But if you want to have it SPD, and if you have been SPD and you want to have it SPD, that's a unique choice, and you can just find this by diagonalization. So if this m, let's just take the square root of m, and m to the minus 1 is the same. If you diagonalize like this, so Q orthogonal and D being the diagonal of sigma 1 to sigma n, and the sigma j are all positive because it's positively finite, then you can set m, let's say, to the minus 1/2 just to Q times the diagonal matrix with sigma 1 to the minus 1/2 up to sigma n to the minus 1/2 times Q. So that is the unique positive definite square root of a positive definite matrix, or the negative, the inverse of the square root. Okay, and now we substitute xn will from now on be called m to the minus 1/2 yn. Okay, also what I forgot. Even though this is not monotone, we can still try to write the proximal point method down. So I forgot to show that here. Let's try to write down the proximal point method, which would be I to the I plus m to the minus 1a to the minus 1 xn. Okay, but it's up. So now it's not really clear if this is it's not even clear if this is an equality here, because we don't know about monotonicity, right? It may be multivariate at that point. I'm going to show that it's not. Okay, so now let's substitute this here. in this equation. So what we get is, so first here we get m to the minus 1/2 yn plus 1 equals to identity plus m to the minus 1a to the minus 1 m to the minus 1/2 yn. Okay, let's decode that guy and bring the inverse to the other side. Then we have m to the minus 1/2 yn plus 1 plus m to the minus 1 a m to the minus 1/2 yn plus 1 includes m to the minus 1/2 yn. Okay, and now we multiply from the left by m to the minus m to the 1/2. So if we multiply from the left by m to the 1/2, this guy cancels, this cancels, so we get yn plus 1 here, we get yn here, and then we have m to the 1/2 times m to the minus 1/2 gives us m to the minus 1/2 a m to the minus 1/2 yn plus 1. And this is the case if and only if yn plus 1 is equal I plus m to the minus 1/2 a m to the minus 1/2 and this to the minus 1/2 yn. So in this here, of course, this is now the resolvent of m to the minus 1/2 a m to the minus 1/2 y. And now here, this operator here, a, multiplied from the left and from the right by m to the minus 1/2, still positive semi-definite operator. That's nice and monotone again, and also maximally monotone again. That's simple to see that this is still monotone. You just have to multiply from the left and the right, and then in the products you can get one over the other side, and so that's pretty clear. Maybe I just show it to you because I think we have enough time. So this m to the minus 1/2 a m to the minus 1/2, that is monotone. If a is monotone. So how does that go? You take let's say u in or ui in m to the minus 1/2 a m to the minus 1/2 xi, and then you take then this is the same as m to the 1/2 ui is in a m to the minus 1/2 xi, and you would like to have now that u1 minus u2 times x1 minus x2. This should be positive, and what you can do now here is you introduce here an m to the minus 1/2 times m to the 1/2 u1 minus u2 x1 minus x2, and then this is self-adjoint. You bring it to the other side, you get here m to the 1/2 u1 minus u2 m to the minus 1/2 x1 minus x2, and of course this goes on both because it's linear, and then you see these guys here, so this one is in there and this one here is in there, so this is positive. Okay, so that's nice. That was I just didn't remember. This is actually actually I'm going to prove here, about to prove lemma 26.6, but anyway, this is monotone, and so it's even maximally monotone if a is maximally monotone. So this proves m to the minus 1/2 a m to the minus 1/2 is monotone if a is so, and okay, that is that exactly like I did here, but with z and okay instead of y. Okay, how about maximality? So if m to the minus 1/2 a m to the minus 1/2 not there would exist, so we could enlarge the graph, so there would exist a pair x and u such that for all v in m to the minus 1/2, a m to the minus 1/2, y, it holds that u minus v x minus y is larger than 0. It's in the lecture notes, and probably not going to show it right here, but this is this you can see by maximality of a. So maximality of a guarantees you the existence of something else, and then you can just rescale it with m to the minus 1/2, m to the 1/2, and then you end up there. So we've just proven something which is called lemma 26.6 over here. If A is maximally monotone on X, M is SPD, then A to the minus 1/2, M to the minus 1/2 times A times M to the minus 1/2 is also maximally monotone. So this, you just have proven this. Okay, and we're almost done already again with the lecture here. So this is all fine and nice, but it sounds like it may be now difficult to work with, right? So if we now choose a precondition m, so this m is called preconditional. Because it turns the equation into something, the inclusion of something else, and this is may make this problem much simpler. We're going to see that in the future, in the next lecture. But if we now have chosen an m, so here we need m to the minus 1, and here we also need the square root, which sounds maybe a bit difficult. Here's another way of seeing this that is actually really, really helpful. So if m is SPD, then this expression here, x, m, y, this is an inner product. On Rn. And this gets the name x, y, m. So any positive definite matrix gives us an inner product on Rn. Like that. So we just kind of rotate and scale the axis somehow, maybe even flip something. So what we can now see is that this operator m to the minus 1a is actually monotone, but not in the normal inner product, but in that inner product. So one thing of viewing all the thing is we move from A to this complicated object here, which is, of course, it's only complicated in theory. In practice, in theory, it's simple, so I'd say like this. But you could also say we move to the object m to the minus 1a, which is exactly monotone again, but with respect to this inner product here. Okay, and then it gets even simpler, because if you do that, there's another simple way to express the proximal point iteration, so the resolvent. And this is this proposition here, 26.7. So if A from x multi-valued to x is maximally monotone, M is SPD on x, then we have first that identity plus m to the minus 1a to the minus 1, this guy here, can be equivalently written as something without any inverse of m at all, and this is m plus a to the minus 1m. So there's no m to the minus 1 anymore. So if you have chosen your m, you can just apply this guy here straightforwardly. And moreover, m to the minus 1 a is maximally monotone on x with this inner product here. So this here, that this is maximally monotone on x with respect to this inner product, this guarantees the existence of and the uniqueness and single valuedness of the resolvent of that operator, now taken kind of with respect to this inner product. So we didn't see it before, but existence and uniqueness of resolvents kind of it depends on the inner product, because the inner product determines the maximum monotonicity. And moreover, we can write this resolvent here like that. Okay. So let's first prove the equality. And probably it's simple if you write x plus is equal to identity plus m to the minus 1a to the minus 1x, and then just rearrange until we are on the right hand side here. So if you rearrange, bring to the other side, it's x plus plus m to the minus 1a, x plus, this contains x. Of course, we multiply from the left by m, so it's mx plus plus a, x plus contains mx, and you see now we are done already. This here is m plus a applied to x plus. So we get x plus is equal to m plus a to the minus 1 m x. So it's totally straightforward and even simpler than before. And now for monotonicity, let's do it like this. So if we have yi is an m to the minus 1a xi, this is if and only if myi is an ax1, and hence we have, so we want to know what is about this inner product here. Let's just write it down, so we can put the m over there. It doesn't matter where you want to put it. So you put it to the give it to the y's. So, and now my1 is an ax1 and my2 is an ax2. So this is one negative, and that's it. Maximality is again not difficult, but it's always a little bit difficult to explain, and it gets a bit messy. Okay, so this opens the door to a lot of things now. So I'm going to show you an example. Maybe I'll also show you a concrete example, because we don't have exercise classes anymore with any new stuff, I guess. So I think I want to show you the practical examples also in the lecture here again. So but using this preconditioned proximal point method, it's a kind of a very, very flexible way to turn a lot of monotone inclusions and a lot of complicated optimization problems into more or less simple sub-problems, such you can really simply implement on the computer. Okay, so that's it for today. And we're going to see, maybe go through the stuff once again, what we've seen here, so that we have a short overview. So what we've seen here is, so we analyzed the proximal point algorithm for maximally monotone operators. For some reason it's still called proximal point, although there's no prox operator involved anymore. It could also be called the resolvent algorithm, but that's not the case. And we've seen, with the help of the notion of co-coercivity, that strongly monotone operators have contractive resolvents. So once you know that, and what we already knew is that monotone operators have firmly non-expansive resolvents. These two things are enough to invoke our general results about Krasnodębski-Mann iterations to show that if you have a maximally monotone operator, proximal point methods converge to a solution if there's one, and if you have a strongly monotone operator, there is always a unique solution guaranteed, and the proximal point algorithm converges linearly towards that. Okay, and then for kind of completeness, we also show the same thing here with variable step sizes, and the proof is slightly different, but not so much. The general steps are more or less the same. Okay, and then finally we talked about preconditioning monotone inclusions, which so I don't know if you know it, but if you want to solve linear equations, so large linear equations on the computer, preconditioning is the way to go. So if you know a good preconditioner of your equation, life can be much, much easier, and these methods make it much, much faster. Here it's the same but slightly different story. The possibility of preconditioning it allows you to turn these some of the monotone inclusions really into practically solvable preconditioned proximal point methods. I'm going to show you the next time, and we're going to work with this formulation here. This preconditioned inclusion, m to the minus 1a, x contains 0, is indeed still maximally monotone if a has been maximally monotone, but on X with a different inner product. But still X stays a Hilbert space here. And moreover, the iteration will be simple in the sense that you only need the M and don't need M to the minus 1. Okay, so that's it for today. And we see you next Tuesday for the second to last lecture.